Alright, we're on chapter 10.2, which is logarithmic functions. And so what we're going to do is we're going to study the inverse of an exponential function. And that's the first thing you guys got to know, is that exponents and logarithms are inverses of each other. So if I take any type of exponential form that you guys are familiar with, let's say I said b to the x equals a. We could identify a couple things. Well, we know that b is equal to the base of the expression. X is the exponent, and a is the answer. This would be exponential form. If I wanted to shift this into logarithm form, I would say log, the base is down here, so base b, of a, which is the answer, equals the exponent. All right, so basically what you're doing is you're kind of reaching into the exponent and you're kind of pulling it inside out, and that's how you get this logarithmic form. Now I know this seems kind of weird, it's a little off-putting. We're going to do a bunch of examples of this right now. I'm just going to go ahead and give you a bunch of exponential forms and we're going to convert them into logarithmic form. So if I said something like 2 to the 4th power equals 16. All right, well the base is 2, so it's going to be log base 2 of the answer, which is 16, equals 4. All right, so again, base, answer, exponent. Let's do another one. If I say 3 to the 3rd equals 27, then what I'm going to do in here is I'm going to say log base 3 of 27 equals 3. And again, I can take this to another level. I could say, if I said 3 to the, let's not do 3 again. If I say 10 to the negative 2 equals 1 over 100, then I can say log base 10 of 1 over 100 equals negative 2. Now, there's something in here that hopefully you guys are catching on to. I'm going to do one more example here. If I say 81 to the 1/4 power equals 3, then it's going to be log base 81 of 3 equals 1/4. Now there's something about each of these answers that I want you guys to keep in mind. Is that 16, 27, 1 over 100, and 3. They're all positive. And that's because, let's think about this for a second. There's nothing, let me just get a number 2 in there. There's nothing that I can put into this box that will produce a negative number. Right? If I plug in negative 5 billion, I'll get a really, really small number, right? I'll get a really, really small fraction. But there's nothing I can do to make this negative or make it 0, right? So we say that logs, so we can say that the domain of log is that the answer must be greater than 0. And when I say the answer, I mean this number here, the red. Must be greater than 0. Must be greater than 0. Must be greater than 0. Scroll up. Must be greater than 0. And in this case, in this general logarithmic form, a must be greater than 0. All right? So that is logarithmic form. And so let's go ahead and do a few different examples of this. Okay, in our first example, we're going to say log base 3 of 27 equals x. Now, if you're ever stuck, just go and just change forms here. Remember, the 3 is the base, the x is the exponent, and the 27 is the answer. So I'm asking myself, 3 to the what power gets me 27? Well, hopefully by now you know that x equals 3, and that is because 3 to the 3rd power equals 27. All right? So let's try another one. If I say log base 5 of rad 5 equals x, well, this is kind of odd. I'm going to go ahead and just change forms here. This is 5 to the x equals, well, rad 5, I can rewrite rad 5 as 5 to the 1/2 power, right? Because 1/2 power is the same thing as radical. And so, since I have the same basis here, I can say x equals 1/2. I'm going to box that one too. If I say log base 3 of 3 equals x, well, I'm asking myself 3 to the what power equals 3? Well, that's easy. X equals 1. In fact, that's true of any type of logarithm when the base and the answer are the same. If I say log base 51 of 51 equals x, well, x automatically equals 1. And that idea is going to come back in a couple chapters in the future, this idea of this canceling to become 1. Okay? Let's do something a little more funny. Sometimes they might give you a base like 7, being raised to the log base 7 of, say, a number like 84. Similar idea here. Any base that's being raised to the log of the same base cancels out and becomes 1, so your answer is 84. Let's up it a notch a little bit with some more tricky equations. If I say, like number 6 here, log base 8 of 3x minus 1 equals log base 8 of 2x squared. Well, here's the thing, is I can go ahead and change forms here. My base is 8, and I'm taking that, remember my exponent is this whole thing here. So the exponent is log base 8 of 2x squared, and that's going to equal my answer, 3x minus 1. Well, remember what we just covered here. Whenever I have the base and the log being raised to the same base, they can get each other out of there, and I have 2x squared equals 3x minus 1. From here, I can go ahead and set this thing equal to 0. 2x squared minus 3x plus 1 equals 0. I just subtracted everything and moved everything over. And I can go ahead and factor this thing. That is 2x and x. I have a negative, and it's going to be 1 and 1. So x equals 1/2, and x also equals 1. Now, I can go ahead and check. In fact, I must check to make sure that I don't end up with a 0 as part of my answer, or a negative number. So if I plug 1/2 into any of these, I think I'm going to be fine. And if I plug 1 in, I'll be fine also, so both answers are going to check out. Now that, number 6 there, was a bit of a roundabout way of doing this problem. There's a faster way of doing it by just recognizing, like in number 7 here, if I say log base 10 of x squared plus 16 equals log base 10 of 80. Instead of changing forms here, because I'm going to end up doing something kind of crazy, I can instead just go and get rid of those logarithms, because since all the bases are the same, they're going to cancel each other out, right? Because if I change forms, I'll end up with 10 log base 10 of 80, and that's going to cancel out. Just go and hit the cancellation right away. So from here, I'm going to end up with x squared plus 16 equals 80, x squared equals 64, and x equals plus or minus 4. Now, I have to check because I have x's as part of my answer, so I need to make sure that I'm keeping within my domain, that this, whatever is the result of this, is going to be greater than 0. Well, if I plug 4 in, yes, that's going to be greater than 0. If I plug in negative 4, well, it's going to get squared anyway, so it's going to become positive. So I think I'm going to end up with something greater than 0. In fact, I know I am. So I think both answers check out. And again, I know they do. It's number 8 right here. So again, we have a situation of log base 2 of 2. And whenever we have this situation going on right here, I can go and get rid of those and have it be 3x plus 2 equals 14. Now 3x is going to equal 12, x is going to equal 4, and all's good. And our last example here will be log base 10 of log base 8 of 8 equals x. Now don't let the compound logarithms kind of throw you off. Remember, log base 8 of 8 simply becomes 1. And I have a log base 10 of that equals x. So now from here I go and change form, so 10 to the x equals 1. Well, how can I turn a 10 into a 1 using an exponent? Well, that exponent would have to equal 0. Okay, I think that just about does it for the logarithmic functions. We'll see you in the next chapter.